I have an experiment here just to show you empirically that the central limit theorem makes sense. So in this case I have two random variables initially. I'm going to keep adding random variables to show you that the central limit theorem is consistent with the reality. So in this case I have two random variables, variable number 1, and I'm going to do the addition between, and this is showing the histogram. So I generate a population of random variable number 1, which is following a PDF which is uniform between 0, suppose in this case, and 1. It could be any value having the same probability, and other values outside this range is going to be 0. So this is a uniform small plateau in a small region, and then I took maybe 10,000 or more samples for generating a population which is represented by that PDF, and then I generate another population and I do the addition for each of the population. I do the addition and I get the resulting random variable fet equal to x1 plus x2, and I do the average divide 2. This is what I get. And then I'm going to see what is the result of that. So I generate many, maybe 10, 20,000 samples of each of the population. And after I do the addition, the resulting, the histogram of the resulting variable set equal to x1 plus x2 divide 2. And I get a histogram which should have a shape similar to that of the PDF describing that random variable. So I got triangular, yes. And then I try, in this case, the average of 3 random variables, each of them having a histogram something like this. And then I did the addition and I got set equal to x1 plus x2 plus x3 divide 3. I get the average. And I start to have this shape. Now this started to give the impression it's only 4 average of 4 samples, and this is the histogram. I'm doing it for it. Now I have 5 samples. I got 5 population, 10,000 elements each of the population. This, corresponding to one of the random variable through depend, according to certain PDF. And then yes, I keep adding. And now the resulting histogram here of set equal to 19, the addition of 19 independent random variables, each of the random variables being represented by a population, like the one that we have here, having this histogram. And yes, the resulting histogram of set is sort of taking a shape similar to that of a Gaussian PDF. So because this random variable is sampling now, or corresponds to samples of a PDF which has similar shape. This is very interesting. So this is verifying for random variables, one dimension, that yes, the central limit theorem seems to be consistent with the reality, and I don't need to have infinite addition. I just need to have, in this case, 20. That is not a large number. Now we have this in 2 dimensions. So again, I have random variable x1. I follow in certain PDF which is uniform between 4 and 6 in x, and between 3 and 5 in y, or this is second, this is y. And in this case, I'm generating another population which is following the same PDF, but doesn't need to be the same PDF, it could be other PDF. And I do the addition, and I get the new population here. The one that you saw before was plenty of point everywhere, because that one was uniform in this range of values. But now, I obtain set equal to x1 plus x2. Yes. Each of them x1 and x2. Random variables following a PDF which is in this case described by this histogram, but it should be completely flat. And then now the shape that we start to see here, is sort of having a shape. This is the histogram which should correspond to a PDF having sort of this shape. It starts to be unimodal. This is adding just 3. And I keep doing that. More 5, 6, 7, 8, 9, 10, 11, 12, suppose. So in this case, it had the effect of having a linear combination of 12 random variables which are independent. Each of them happen to have a statistical description according to certain uniform PDF. So in this population, which correspond, I don't know, to variable x12, so yeah, this is the histogram. It's always sort of a plateau, because this random variable or this population corresponds samples of certain random variable whose PDF is uniform in this range of values in x and y. But after doing the addition and getting the average, I start to get a population which is concentrated in a certain area, which is, if I represent that population through a histogram, it will be something like this. If I use this histogram to recreate certain PDF, it will have a shape like this one. What is telling us this thing? Well, it seems to be that the central limit theorem is right. I didn't need to have an infinite number of addition or a linear combination with infinite components, each of them being a random variable. Just in this case, even before 10 was already producing a PDF which is sort of Gaussian. So in our case, that means that when we keep using all these measurements, each of them which is being polluted by certain random noise or uncertainty, all these things which may have PDF which could be Gaussian, it could be uniform, and different parameters, even some others that don't need to be Gaussian, they don't need to be uniform, it could be more complicated. But in our estimation process, because we are combining many of them, the result seems to be not going to be a linear combination, it's going to be a non-linear one, but still combine many, so that our result in random variable, which is what we're trying to guess, represents certain physical variables, from our perspective being a random variable, that one may very likely to behave statistically as a Gaussian PDF. So the more we combine information, the more Gaussian it should get. So that is why Gaussian are so attractive. Not only because this, we could see and we could predict in theory through the central limit theorem, is that is in terms of processing, playing with Gaussian is so convenient, so efficient, that is very attractive. But we have a good reason to consider that assumption to be very realistic. Alright, so we stop